In this video, we're going to look at the motor effect, which is a higher tier topic for AQA GCSE. So the most important principles that we really need to get students to remember is that if we have a current carrying wire, then it creates a field around it, or it creates a magnetic field around it, which is this circular field, and we can find the direction of that circular field by the right-hand rule. If this is placed next to a permanent magnet, so if placed next to, or I'm just going to say another magnetic field, because it doesn't necessarily have to be a permanent magnet, it could be an electromagnet. What will happen then? It will interact with that field. And how could it interact? It could attract or repel. And then this movement, all right, from the attraction or repulsion equals the motor effect. So it's the fact that a current carrying wire in a magnetic field will experience a force, and any movement is the motor effect. So this could simply be a single wire placed in a magnetic field like this, and it will move. That's the motor effect. Or it could be something much more complicated with coils of wire in a magnetic field that actually spins round and is much more like a typical motor that we would think of. How do we work out the direction that this wire will move? Well, we need to use Fleming's left-hand rule. So this is usually quite a fun bit of lessons, and when students come to answer these questions in the exam, almost every year the invigilators get a bit worried. They think students have gone a bit crazy because they're waving their hands about in a weird way. And you can really build a nice story into your lesson about this and make it memorable for students. So how does this work? You need to get your left hand and you need to put your fingers like this. You need to put them all at 90 degrees to each other, or the first three, or you could describe them as all orthogonal to each other. That means all at 90 degrees to each other. And then our different fingers represent different things. So our thumb, I'm going to write on my fingers, and I'd encourage you to get students to write on their fingers too in the lesson, because it does help them remember. The thumb is the motion or the force that is experienced by the wire. The first finger is the field, and the field, importantly, is north to south. And then the second finger is the current, and the current is always conventional current, so positive to negative. So then in an example like this, we need to align our fingers. We need to put our first finger where the field is going, so the field is going north to south. Our second finger the way the current is going, this way, and in that case the force will be up or out of the page. And a reminder that out of the page sometimes is represented like this, and into the page is represented like this. Although strictly this isn't 100% out of the page, this is just up, and up would be fine. Out of the page would be literally towards you. So there's a few other tools for remembering this, and I personally don't have a preference when it comes to using these. I think you just need to see what your class responds to, or if they have another way. One way is to really highlight the fact that letters in the words actually match up. So thumb is motion, first finger is the field, and the second finger is the current. This works for some students. This is personally how I remember it. This one requires a bit of theatre, but you kind of really dramatically, go stick them up. The FBI is here, and then F for the first thing in FBI is force. B is the symbol for magnetic field. Second one, and the third one is current, is the I in FBI. For some students, this works really, really well, but it does require some drama from you. And then the third one, Manchester Football Club, a nice mnemonic here. M for Manchester, F for football, and C for club. There are plenty of other ones, but these are the three most common ones that usually work fine for students. So what do we need to know about motors? Well, the spec, quite interestingly, is actually quite vague in its description. The spec says, explain how force on a conductor causes the rotation of a coil, and it also talks about a simple motor. So it doesn't really talk about DC or AC motors, and it doesn't really give information on the level of detail you need to go into. So probably a lot of what I'm going to talk about now is a little bit more than is needed. And certainly the exam questions I've seen about typically talk about the direction that something will spin, the direction of the force on the wires, and then a couple of other points. So the couple of other points is always how do you reverse the direction of motion? So this is really easy. You either reverse the direction of the battery, so you're switching the current direction, and obviously if you switch the current, you're flipping the force over, or you can reverse the direction of the magnetic field by just simply flipping the magnetic field around or the magnet around, and again you can see that flips the direction of the force. Sometimes one of these is not appropriate, sometimes this is not appropriate depending on the way that the diagram is drawn, if these magnets are fixed. The other important sort of wordy question is how do you make it spin faster? So we're talking about something like this. So what we need to do, we need to increase the force on the wire. So we need to think back to the equation that governs this whole situation, the force on a current carrying conductor, the magnetic field or magnetic flux density times current times length. So what we need to do is we need to increase any one of these three things. So to increase the magnetic flux density, we could simply use a stronger magnet, which you can replace a bar magnet with a neodymium magnet, for example, or an electromagnet. So interestingly, if you take a typical fridge magnet, then its magnetic field strength is very, very small. It's around 0.005 Tesla, right, which is tiny. A neodymium magnet, which are they're quite recent discovery actually. The really strong ones that can actually be quite dangerous even when they're only sort of this big. That will probably be 1 to 2 Tesla for the average one. The Earth's magnetic field is extremely weak, 40 times 10 to the minus 6 Tesla. So we're talking about micro Tesla, which makes it even more amazing that things like birds actually use this to navigate. It really, it shows how amazing evolution is. And at some point in this unit, it's worth talking about, animals that can sense magnetic fields. I think sharks also sense magnetic fields. And then the fun fact that students always love is the field that's needed to levitate a frog. And if you can watch my video on magnetism, and I briefly talk about diamagnetism here, is about 16 Tesla. So really all the values of B are very small. But to increase it, we can use a stronger magnet, or what we can also do is move magnets closer together. So this doesn't apply in every single situation, but if we have 2 magnets here compared to the same magnets here, the field here is going to be a lot stronger than the field here. To increase I, well, we can, usually it's enough to say increase the current. that's usually enough. How would we actually do it? It would actually create a larger potential difference, which would increase the current. So sometimes it's acceptable just to say increase the potential difference, but we should talk about current because that's what's in the formula. And then length, we can make a longer length of wire in the magnetic field. So put a longer length of wire in the field, or a sort of another way of saying this is we can use more coils. So you imagine a situation like this, right? We've got a fixed magnetic field effectively. The magnetic field, is going to be pretty negligible past sort of here. So if we actually start to put coils, then we can actually bunch the coils up on top of each other, and we could get thousands and thousands of coils in the same area, and therefore we've massively increased the length of wire. So let's look at some motors. So something like the Boardworks Animation, which this is incredibly useful here, because you can have it spinning on the board and you can really talk through every single part of it. So if you start it playing, what you can do is you can say, right, well, obviously when there's no current flowing, it doesn't move. You can turn it on. You can use Fleming's left-hand rule. You can trace the current here, and you can trace the path of the current, and you can work out the direction of the forces. So we've got an end-on view and a side-on view. So follow the path round, use the left-hand rule. So this is a DC motor, and you'll notice that in this part here, this is called a split ring commutator, which means that the positive current always ends up flowing round this right-hand coil on this side. So it goes around the orange bit, around the right-hand coil, which means the force is always down. And you can see that the arrows flip as it goes past vertical. So this is important because then it will work with a DC current. We've always got the same force, the same current. This is probably more detailed than students need to know, but it's worth teaching them with a bit of a stretch. So this is different to an AC motor. So we've got two diagrams here. We've got on the right hand side, we've got the AC motor with the split ring commutator, and an AC motor on the other side just has two carbon brushes. So the positive side always goes to the same brush, which means the current is always going the same way. So if we had a pure DC source here, then the motor would spin, get stuck halfway up, and then it wouldn't move any further because the force would be in the wrong direction. This is why we need an AC current, which means that when it gets to vertical, the direction of the current flips, and therefore the direction of force flips. Whereas with the DC motor, we've got that current flipping because of this break here. And you can, this is not on combined science, this is a triple science now, but you can talk about generators, and you can see, there is no difference between motors and generators. The only difference is that a motor, we put in electricity and we get out motion, and in a generator, we put in motion and we get out electricity. But otherwise, they work exactly the same, down to the level of split ring commutators or slip rings and carbon brushes for an AC generator. And then you can talk about, the challenges of creating that motion. Do we want to do it by fossil fuels? Do we want to do it by, wind turbines, etc.? So it's just a nice little thing for the more able classes, or obviously you have to do it triple science. And one final thing, we should do lots and lots of practice with Fleming's left-hand rule and working out the direction things are going to move. So it's worth spending a good few minutes on this simulation with the force arrows on, and students using Fleming's left-hand rule. And then it's worth giving them lots of examples. I'd always put these on separate slides for students, but you can see from different exam questions just how different the diagrams can look and it can really confuse students unless you actually spend, a good 10 minutes in class going over lots of different examples. So in each of these, you get them to hold up their left hand, move it about, work out the direction of the force. In an exam or when they have it on paper in front of them, tell them to change the paper around to match the direction of their fingers, because then they don't have to contort themselves. So what I'd recommend you do is pause the video now and spend a minute working out the direction of the force for each of these wires. So the first one obviously has been done for you. This orange arrow is on there. And then these are the direction of forces on each of the other diagrams. In terms of demos that we can do for this, there's loads of nice demos. I'll link to one or two in the description. We have actual motors. We have motor kits that students can make themselves. You can make a simple motor called a homopolo motor using a battery, a magnet, a screw, and a piece of wire. That's really nice for students to see just how basic this is. And the more you emphasize this is basic and easy, the more students believe it's true, and actually the better they do. We also have a device which is basically two parallel wires and another piece of metal that can spin when you put a current through it, and that's really nice for demonstrating Fleming's left-hand rule. And then there's also a really nice speaker demo, which is just simply a piece of wire that moves up and moves down when you put an AC current through it, and if you move it fast enough, you actually have made yourself a speaker. And it goes to show just how simple speakers are. And then if you've got time in an able class, you can talk a little bit more in depth about how speakers work, or the opposite motors, sorry, not motors, microphones, because they are effectively exactly the same. It's just like, the difference between motors and generators. We're either putting electricity in to get motion out, or we're putting motion in to get electricity out. But like a few things here, microphones and speakers are triple content